Today we're going to look at two special numbers, starting with the golden ratio. So we start with the 5 gon. Let us remember how we compute chords and lengths of chords. So the outer angle, meaning outside the pentagon, is governed by 360 divided by 5, so P equals 5, and that is 72 degrees. So the large angle inside the pentagon is 180 minus 72, which is 108 degrees. But we only need the 72 degrees. Now that means that the two smaller angles, which are both equal inside the pink triangle, they are equal to a half of that, which is 36 degrees. Now if we use the sine rule on the pink triangle, and note that all the triangles of that type inside the pentagon are of course the same, then we compute the length of the chord. And that's just the sine of 72 divided by the sine of a half of 72, which is 36. And that is the golden ratio, 1 plus square root 5 over 2. Now notice that we could use the same argument for any polygon. So if we took a polygon with 10 sides rather than 5 sides, then we're dividing 360 by 10 rather than 5. And the length of a chord is going to go to sine of 36 divided by sine of 18. And that's another special number which we call rho, which is the square root of phi plus 2. The lengths on a golden rectangle include rho as at the diagonal. Starting with the 108 degrees, if we halve that and get 54 and use that instead of the 36, then we naturally calculate the ratio of rho to phi. Taking the hexagon instead of the pentagon, the analogue of the rho of phi would equal 1. You can easily check that. Recall that 1 over phi is phi minus 1, and so rho over phi is rho phi minus rho. And if we take all these numbers with rho and phi in them, we're interested in numbers of the form a plus b phi plus c rho plus d phi rho, where a, b, c and d are whole numbers. We claim that most physics can be done with this set of numbers, along with a few other numbers like square root 2 and square root 3. The set of numbers with just the phi and rho form a dense subset in the reals, and whereas the reals are problematic from the point of view of logic, these numbers act very nicely. We often look at changes of scale, that is fundamental in particle physics, and here what we have are two squares. We have a small square of side length phi and a whole lattice of those small squares at a 45-degree angle to a bigger blue square lattice where we see the side lengths here are phi cubed, and phi cubed is just 2 phi plus 1. The numbers phi, phi cubed, rho and rho cubed are related here very easily, and we see that in the case of rho we get the sum of the inverse tangents equaling 4 pi over 5. Now 4 pi over 5 is a very special angle because it turns up in the mathematics of something called the Fibonacci anion. Now when we draw ribbons for particles, which is something we've been doing all along, those ribbons belong in this mathematical universe for Fibonacci anions. What we're talking about is the theory of quantum computers. And these quantum computers are playing around with the numbers we've just been talking about, doing quantum logic, which is about the experiments that we're doing and thinking about as experimenters, as observers. And we're doing all of that without an enormous amount of baggage, which make it much harder to understand. This is all very simple.